Hi, my name is Summer, and this is my lab report on magnetic braking with Faraday. The purpose of this lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet or tube interaction computationally on GlowScript, and then compare our computational predictions with our observed data. Faraday's law is a magnetic flux that changes time to create a non-Coulomb's or Curly electric field that generates an EMF or voltage. The negative sign in Faraday's law is called Lenz's law, and it is summarized as nature abhors a change in flux. The magnetic field of a bar magnet is calculated using this equation. The change in magnetic flux that generates an EMF can be caused by either a change in magnetic field, a change in area, or both. The electric field produced by the change in magnetic flux, which is represented by this equation derived here, follows the loop and is in the same direction as the current. The changing magnetic field and resulting change in flux induces a current in a loop of the tube and is explained by Ohm's law. To consider the magnetic force on the loop, the equation is derived as shown. The velocity and position update formulas are used to model the motion of the falling magnet computationally. The main results of this lab was that the average time for the magnet to fall through the tube experimentally was 1.36 seconds. The simulated time for the magnet to fall through the tube was 1.141 seconds. For the experiment, one person held the tube vertically and positioned the magnet right above the top opening. I held my phone and recorded the magnet entering the top of the tube and leaving the bottom on video. I recorded the time when the magnet enters the tube and exits the tube. I calculated the time it takes to the magnet to fall through the length of the tube. We repeated this experiment 5 times and then calculated the average time it took for the magnet to fall through the tube. The system in this experiment is the bar magnet and tube, and the surroundings is everything else. Here is the data collected from the experiment. The average time calculated from 5 trials was found to be 1.36 seconds. For the computational model, I have the initial conditions and constants set. I implemented the formula into the code to calculate the magnetic field of the bar magnet. Next, I created a function to calculate the magnetic flux using the equation to find the rate of change in magnetic flux through each ring caused by the falling magnet. I used Faraday's law to calculate the current induced in each ring by the falling magnet, and then used the Biot-Savart law to calculate the force exerted on each current carrying ring by the falling magnet. Then I used Newton's third law to calculate the force exerted on the falling magnet by the whole tube of current carrying rings. I calculated the net force in the magnet by summing up the magnetic force and gravitational force. Finally, I used Newton's second law to write position and velocity updating code to model the motion of the falling magnet. This is the simulation created by the code and the graph of the motion of the bar magnet as it falls through the tube. When the graph slopes downward, the gravitational force is greater than the opposing magnetic force, causing the magnet to accelerate. Towards the middle of the tube, the gravitational force and magnetic force balance each other, causing the magnet to move at a constant velocity. The magnet was in the tube for 1.141 seconds, which differs from the experimental time. According to Lenz's law, induced currents oppose the change in magnetic flux that caused them, so red corresponds to counterclockwise and blue corresponds to clockwise. As the north pole of the falling magnet enters the tube, the top ring wants to oppose the increasing magnetic field, so it induces a current that creates its own magnetic field upward, opposing the downward magnet. Thus, to create the upward field, the induced current must circulate counterclockwise. If I were to flip the magnet around, the polarity reverses, so the south pole would enter first instead of the north. This means that the direction of the induced current would reverse because the change in magnetic flux is opposite. Thus, the red and blue regions would flip. In the real world, the magnet falls more slowly at 1.36 seconds than in the simulated system, which was 1.141 seconds. There is a small difference, but this difference can be due to factors such as air resistance or friction. The computational system can be made more accurate by accounting for air resistance or drag force and human errors. The shape of the velocity versus time plot tells us that the initial drop is primarily due to gravity and that there is very little opposing force, so it accelerates. But when the curve levels off, the velocity stays constant for some time due to the balance between the magnetic force and gravitational force. If the resistivity of the conductor was nearly zero, the induced currents would flow with almost no resistance, creating stronger opposing magnetic fields. This means that the falling magnet would experience more magnetic drag and would fall even more slowly. If there were holes or slots cut into the tube, this would disrupt the path of the currents, breaking the continuous loops needed for strong current flow. This would weaken the induced magnetic fields, decreasing the magnetic drag on the magnet, letting it fall faster through the tube. Some sources of error in this experiment could be that we might not have always dropped the magnet from the north side, or that the time wasn't precisely measured. Additionally, if the magnet wasn't dropped perfectly centered, it could have hit the tube sides, slowing it down.